Hey everyone and welcome back. This video is going to pick up right where the last one left off. So if you're coming to this video totally fresh, you may want to go and watch the last one and maybe even a couple before that. Because we've spent the last few videos working directly with nodes. We've been linking them and deleting them, searching and navigating through them. But the truth is, a bunch of nodes chained together like this is still not actually a linked list. It's just raw memory with pointers. This is actually just like arrays. An array by itself isn't an array list. It's a low-level storage mechanism. What makes an array list a real data structure is the wrapper that exists around the array. Today, we're going to do the same thing for nodes. We're going to take our pointer operations and turn it into a real linked list class. So the very first thing we're going to do is review the code that we have here, and then we're going to go through the difference between nodes and linked lists. And this definition is really important because it is going to tie into next week's topic as well. So this really is picking up where we left off. We have the delete by value, delete at, and delete top. In addition to the deletes, I've gone back in and recreated our insert top, insert at, and insert tail methods. We have our print list method. I've recreated our count and our index of search method. We still have that initialization. And of course, we have our node class down here that has not changed at all. So as we can see, when we're holding a reference to a node like top, what we're really holding is a memory address, the location of the first node, and each node points to the next, right? This alone doesn't give us stuff like a size, a consistent behavior mapping, safety checks, easy ways to insert or remove, protection from broken pointers and nulls, or really any guarantees about how the chain of nodes is being used. It's exactly like having an array sitting in memory with no array list around it. It works, but every single time we want to do something, we are rewriting all of that logic ourselves. Thank goodness we have array lists. So a chain of nodes is a linked structure, but it is not a linked list data structure yet. To get an actual data structure, something students can actually reuse without rewriting the pointer logic every single time, we need to do exactly what ArrayList does to arrays. We need to wrap our nodes in a class. Let's get right into this. So it's really about transforming what we have here into a linked list class. Let's go ahead and add this linked list class. Now, typically when we add a linked list class, what we actually end up doing is pulling the node class internal to the linked list class and making it private. By doing this, it will allow us to actually get rid of the modifiers on the variables, which means we don't need all these getters and setters and all of this stuff. It can all be used directly as properties from within the linked list class, and that can just save us a lot of headache. It's a nice thing to be able to do. You don't even really need constructors either, because you can just reference everything directly and use a default constructor, but I intend to leave the constructors just for clarity purposes. Now we can close this up and understand that we have access to our nodes, the nexts, and the data directly from within the linked list. And now we can make a private node top that lives inside this linked list class. And we can start to move all this data internal to here and really create this wrapper class just like an array list. So for example, we can add, of course, a constructor. And when we create a constructor, all it does is set top to null because there's no data being made yet. Now, in order to make data, we're going to need our inserts. So I'm actually just going to grab all three of my inserts from up here and bring them into my linked list class. Now, this is a non-static context, so we do need to get rid of the word static, just like that. We also don't need to pass in top anymore because we have access to top right here inside the linked list. There we go. Lastly, we don't need to return top because top already lives, again, inside this linked list. So this is about to get a lot cleaner. This one has to change like this. There we go. So now we can just reset top when we're inserting at the top. Top only changes if we need it to here. Top only changes if we need it to here. Perfect. We've now moved all three of our insert methods into our linked list. Let's keep going. Let's move our delete by values into our linked list. Same thing. We don't need to actually return anything anymore. We just need to set top equal to a value. So this becomes void and non-static. This also now can become void and non-static. And this can become void with non-static. Now there is some common return values for things like insert and delete, but we'll talk about those once we get everything moved in. Let's move our search in. There we go. This can be removed, but it still does return the integer because it is still a search. And let's move our print in. Oh, did I remove the node top? I didn't. Got to get rid of all those too. Get to clean this up a lot. There we go. We can remove this. This will still print the whole list. We can even bring our count in. Whoops. Right here. All right. We won't bring our init in, but we will change it. A few things here do need to change because I got rid of all those get next methods. We don't actually need any of this anymore. Anywhere that it says get next, I actually just need to replace with the word next now. So I'm just going to do it all at once to make my life a little bit easier. I didn't have a get data, so that was never an issue. I did have a dot is equal, and I could leave it if I want to. It just means I need to put the is equal back in here. Public Boolean is equal int data. Whoops. Return data. This dot data is equal to data. So we can actually leave that in. That's okay. We also have some set nexts that live in here, but not as many as we had for get nexts. So let's just go and find those set nexts, because anywhere I have a set next actually just needs to be, I guess, what'll be the easiest way to do this. Anything that looks like this as a set next just needs to become a dot next equals with a space. We'll replace all of those. And then we've got these left hang around brackets. Now let's just finish tidying this up, make sure it works, and then let's get it to look consistent with what an array list actually gives us. So instead of the init list being the way it is, we'll have a linked list that is called like this. This can now return an entire linked list. We'll come in here, and this will make a new linked list equal, actually, yeah, this is fine, to a new linked list. And now this looks very different. We can just say list dot insert top, and we can get rid of this and this. Once we've done all that, we can also add in our print list function. And we can see if this is a minimally working example. And I'm genuinely not sure. I may have made some more compilation errors. So let's just give it a try. Oh my gosh. I must still have some context specific stuff here. So let's go to Java 140 and see where the heck I left things behind. Oh, I left behind the word static. Okay, how much of that gets fixed? Oops. Without the word static. Okay, and then, oh, we have a delete top that no longer has any parameters, but I left some parameters behind. I told you this might happen. We can fix this. Insert at top. That doesn't need to be there anymore. Insert at top. Count doesn't need this anymore. Cleans up our code a lot to not have to pass top around everywhere, you know? Let's see. Did I fix them all now? How many are left? Oh, we're getting closer. Oh, yes. Now, for these, we don't actually have to do it like this. We can just say insert top. Insert top. Because these no longer return anything. Boy, things get much cleaner when we have this wrapper class. That's going to be the like take-home message here. Is things are just getting cleaner, and that's a good thing. Let's see now. Almost there. Delete by value has something weird going on. Oh, yes. My original main is going to be very different now. Let's go ahead and get rid of all of our old main. There we go. Perfect. Now that we've cleared up all of those errors, we can now see that our list is getting populated and printed, only now it's happening through this list variable. I have now made sure that it works using insert top. I could make sure that I test a few other things here, like maybe we test a delete top. Just to make sure that nothing got broken when we did this changeover. Good, top deletion works. Hopefully, I'm not going to sit here and test every single one, but that is something that you could do just to make sure that things are coming along nicely. Okay, so now we've moved everything into this wrapper linked list class. Let's move our focus there for just a second. Now, if we think about our array list and what methods we might have access to through our array list, we have things like add front. It's not called insert top, it's add front. Or perhaps we have, instead of an insert tail, it's actually just called add or insert. And then if we want to add in a specific position, same thing, it's actually just called insert, right? We have add by a single value like this, or add with an index like this. Both exist. We have insert. Let's do consistent naming here. Add. Anywhere we have the word insert, it needs to become add. That's going to be a terrible idea. Let's just do it one by one here and make sure that we change them all. This just becomes add. What did we call it? Add front. Add front. And this just becomes add front. So those are our two different add scenarios. In delete, we can do something similar. It's actually just called remove. Now, if we remove with just a single element, we're going to be removing by value. Remove first. I don't actually know if that exists. In a list, there's a good chance it actually would be a little bit more like calling remove with the value or calling remove with the index. Oh yeah, remove gets tricky because in our situation, if you remember from our discussion around array lists, because we're dealing with ints versus integers, that actually can get really tricky. So let's leave this as a remove by, and this can be a remove at. And then we can just combine our remove like this. If the index is 0, and then we don't need a delete top anymore. Now it aligns a little bit nicer with what we would expect. Alternatively, we could leave it as a delete top in both of these scenarios, delete top, but make delete top a private method because that actually isn't something that ArrayList gives us access to. So we don't want our linked list to give us access to it either. Remember, the whole point is to make this actually look a bit like an array list. So now we have a remove by value. We can have a, we'll call it, I guess, remove at index, and then our hidden remove top method. Really want to get the naming as consistent as I can. There we go. We have a remove top, good. We have our index of, that's already named as expected. Typically, count would be size. That's a bit more common. We could make this even better and smarter by keeping track of our size as we go. So our size starts at 0. Every time we add, our size should increase. Make sure you don't accidentally double increase. If we do an increase in here, it shouldn't increase over here. Do an increase over here. Got to be careful not to do that double increase anywhere. If we do a decrease, one way or another, as long as it's not null, we can do our size decrease here. One way or another, as long as it's not null. If we remove top, we do a decrease. We don't do a decrease here. We only do a decrease here. I guess I can put it at the end. There we go. And now, when we do our size call, we actually can just say return size. That's a lot more efficient. If we wanted to go all the way in that direction, you could even now start to change things like, not that one, but like root this one from if top is equal to null to if size is equal to 0, right? So we can like really start to make this look more like an array list if we wanted to try. There are two more common methods that often exist in our array list that I'm going to add in. There is a check if the list is empty, public boolean is empty, and this just checks if top is null, true if it is, and some kind of a get for the values. So if we get by an index, there we go. Now this one as a get by index is basically the opposite of an index of, right? That one gets the index by the value. This one gets the value by the index. We do need to sort of do the same checks that we did previously. If the index is greater than our size or the index is less than 0, we have to throw some kind of an exception. Invalid index. We are out of bounds. But in all other scenarios, we can just go to that index, get our position. While our position is less than our index, get that cur variable going at top. Cur is equal to cur.next. And then at the end, we can just return whatever that data point actually is. These are the equivalent of the array list methods, but now we're implementing each one as a linked structure instead. Now the outside code, meaning our main method up here, does not have to manipulate nodes directly. It asks the list to do the work, and then the list can keep itself valid. We can prevent things like invalid deletions and null pointer mistakes or broken chains because now the linked list controls all of its own pointer updates. It's really important that we understand that linked lists and array lists are not actually different ideas. They are two different implementations of the same concept. So if we zoom out a little bit, here's what we have. We have array lists being a continuous block of memory wrapped in this behavior, right? It's an array plus this wrapper class that defines all these behaviors, also known as an API, something we will explore next week. Then for our linked lists, we have our nodes plus our wrapper. It's a scattered change of nodes wrapped in this API. They differ in performance and in layout, and they differ in strengths, but they both behave like a list. And that word, list, is the star of next week's lesson when we talk about interfaces and abstract data types. Today we made a huge conceptual jump. from raw node manipulation to an actual linked list data structure. We've learned that nodes alone are just low-level storage, just like arrays, and a linked list class provides structure, safety, and consistency, just like array lists. We moved our pointer operations into methods so that we could control how the list behaves and how the user or the main can access it. We really have defined this parallel relationship between array and array lists and nodes and linked lists. This transformation from memory mechanism to data structure is the foundation of what we need before we introduce abstract data types next week. Next week, we are going to do that. We're going to look at the list abstract data type and discuss some other data structures that we can now implement, understanding this difference between array lists and linked lists. And we can see how these structures are going to fit into a bigger picture of additional data structures. Thanks, everybody, and I will see you in the next video.